Hi friends, in the continuation of data science interview question answer series, we are moving to question difference between linear model, non-linear model, relationship modeled. Linear model assume a straight line or flat plane relationship between input and output variable. Non-linear models can model complex curved or arbitrary relationship between input and output variable. Equation form linear model output is linear combination of inputs y equal to beta 0 plus summation of bi xi. Non-linear model output is function where parameters are not linearly related to input y equal to fx theta. Interoperability linear model high parameter bi directly indicate the change in y for a unit change in xi. Non-linear model low complex decision surface make it hard to attribute predictions to a specified input feature. Bias variance linear model tend to high bias and low variance, often underfitting complex data. Non-linear model tend to have low bias and high variance can easily overfit complex data. Computational cost linear model generally low and fast to train, often having closed form solution. Example OLS. Non-linear models generally high and slow to train, requiring iterative optimization. Example gradient descent. Explainability extensibility linear model limited in modeling capacity unless features are manually engineered. Example polynomial terms. Non-linear model highly expensible and can learn complex feature interactions automatically. Decision boundaries linear model a straight line or flat plane hyperplane that separates classes. Non-linear models a curved intricate or arbitrarily shaped boundaries. Example linear regression, logistic regression, linear SVM. Non-linear models, decision tree, neural network, KNN, random forest, kernel, SVM. Good question. Difference between clustering and classification. Difference between accuracy and F1 score. Formula TP plus TN divided by TP plus FP plus FN plus TN. For F1 score, 2 minus precision dot recall divide by precision plus recall score. Accuracy measures overall correctness across all classes, both positive and negative. F1 score measures the performance on positive class, how well the model performs when the positive class matters. Handling imbalance, accuracy poor matrix for imbalanced data set. A model that always predicts the majority class can have high accuracy. F1 score excellent metric for imbalanced data set as it ignores true negative and focuses on the minority class performance focus. Accuracy focuses on minimizing total error FP plus FN, false positive and false negative. F1 score focusing on minimizing the harmonic mean of false positive and false negative. Output interpretation accuracy a score of zero point 0.9 means 90% of all prediction were correct. F1 score the score of zero point 0.9 means there is an optimal balance between the model precision and recall. Matrix type accuracy semantic systematic metric penalize misclassification equally regardless of classes. F1 score a symmetric metric that emphasize the balance between two other symmetric metrics. Max value accuracy 100% of all prediction are correct. F1 score one perfect precision and perfect recall use case accuracy used when classes are perfectly balanced and true positive or negative are equally important. F1 score used when the dataset is imbalanced majority minority classes and use need a balance between missing positive and misclassifying negative. Moving to question, difference between model drift and data drift. Core problem, the model drift, the relationship between the input feature and the target variable changes over time. Data drift, the distribution of input feature themselves changes over time, but the relationship py is intact. Impact on the model, the model's learned coefficient weight becomes outdated and performance matrix accuracy degraded significantly. Data drift, the model is fed data that fall outside its training distribution, leading to less reliable prediction and potentially performance degradation. Cause model drift, external unrecovered changes in the environment or user behavior. Example, a change in customer preference, new economic condition, a pandemic. Data drift, change in the data generation process. Example, new sensor calibration, a change in user demographics, a new version of mobile app. Detection, model drift detected by monitoring the model's prediction accuracy or loss on live labeled data if ground truth is available soon. Data drift detected by monitoring the statistical properties mean, median and standard deviation of the live input feature and comparing them to training set. Mitigation require retraining the model on newer data that capture the new relationship PY and L granularity. A fraudulent shift in the concept of the model is trying to predict data drift, a shift in the covariance or input variables. Example, a spam filter that was trained to spot old keyword no longer catches new evolving scam messages. Data drift, a model trained on sensor data where the sensors were recalibrated, causing all input values to be systematically lower. Role in ML ops, model drift, a critical performance related monitoring issue. Data drift, a critical data quality integrity monitoring issue. Difference between recurrent neural network and transformers. Core mechanism, RNN recurrence sequentially processing loops and hidden state vector for memory. Transformer self-attention mechanism calculating the importance relevance of all other token to current token per parallelization RNN poor inherently sequential processing makes parallel computation across the time dimension impossible. Transformer excellent self-attention calculation relationship for all tokens simultaneously, making it highly parallelism. Dependency modeling model local short-term dependencies well but struggle with every long sequence due to the vanishing and exploding gradient. Transformer excellent at modeling long-range dependencies because every token can directly attend to every other token. Computational cost, RNN lower cost for short sequence cost scales linearly with sequence length. In transformer, higher cost for short sequence cost scale quadratically with sequence length L2 due to attention matrix. Key limitation, RNN cannot fully capture context across very long document, 500 plus token. Transformer quadratic complexity limits the maximum sequence length it can handle practically. Example 512, 1024 or 2048 tokens. Model type typically used in an encoder decoder setup for sequence to sequence tasks. Transformer can be used as decoder only GPT for generation or encoder only BERT for classification. Training speed, RNN slower to train a large dataset due to the sequential nature. Transformer much faster to train due to massive parallelization on modern GPU TPU use in vision. RNN less common, sometimes used for video sequence analyzing. Transformer increasingly popular vision transformation VIT for complex image classification and generation task. Please like, subscribe and share the channel. Thank you.